All right. Well, I am glad that you're all here, or whatever. I'm not surprised, but nobody else showed up for this extra little class session. So, um, you know, you guys have busy schedules, and it works out that this works for me and not for you guys. But want to make sure that you guys all get your full educational bang for your buck, that you get all of the time that you need to in this class. And so, again, what we're doing. Recording this extra session. This is Monday night, Monday afternoon, and you should not come to the campus and expect new class content on July the 8th, July the 9th, or July the 10th. Looked like enough people were interested in doing the extra little 20 minutes. Still need to talk with university marketing to see if that's going to happen. But yeah, so I guess we'll just jump into it. Look for some homework and homework assignment stuff to come out, and we'll try to just get into this, give you about an hour, 10 hour and 20 minutes worth of some extra material, working through some more node and mesh analysis. So let's review what we talked about, what would have been earlier this morning, or later, whenever, yesterday, whenever you happen to be watching this. So, all right, PowerPoint slides. We started talking about nodal analysis, which allows us to use Kirchhoff's current law to determine the unknown circuit values, especially what we're looking at are these voltages at the nodes within the circuit. And then we're going to start looking, I think we should be able to get into mesh analysis, which is using Kirchhoff's voltage law. We're going to start introducing these loop currents as analysis tools, and that will allow us to determine unknown circuit values. And we started this morning looking at the nodal analysis. As we kind of cruise through here, what we're going to do is we're going to write these equations that allow us to figure out what the voltage is at any node within the circuit. Once we understand those node voltages, we can figure out anything else. We can figure out the voltage across the resistor. We can figure out the current flowing through the resistor by dividing the node voltage by the resistance, whatever we want to do. We can do all of that very easily with the node values themselves. We looked at some examples of how that goes, and this is really the key thing for all of these node current things. When you want to know the current that's running through a given node, it's going to be given as the voltage on one side minus the voltage on the other side, and divide that by the resistance between them. So if we have what this particular equation is getting at is this idea that we might have, let's see if I can get this onto the right. We have two nodes. We can call them, let's see, make this have a resistor between them. This is node M, this is node N. And if we know the voltage at point N, M, and we know the point at N, and we divide that by the resistance connected between them, we can figure out what the current I is that's flowing between those nodes. And again, the way that I'm going to encourage you to always do this is to think about it in terms of I am at node M. I'm writing the equations for node M, and so I'm going to put M first in my equation. If I move on to node N, I'm going to put node N first in my equation. And it works out mathematically that doesn't give us anything strange. So, one of the things that this, in our example earlier, we knew what all of the voltages were and we could solve for some of them. The only node that we actually always know the voltage at is the reference node. We're going to call that 0 volts all the time, and it's going to make some of our equations a little bit simpler too. We looked at independent current sources, and the stuff on this slide correlates directly with the example that we did earlier. And starts walking us through all of this. What you end up with is two, or if you have n nodes in your circuit, you're going to need n minus 1 simultaneous equations to solve for the node voltages. The reason for the minus 1 is that we know the reference voltage is 0. So we have those simultaneous equations. We can solve them in whatever manner makes sense to you. whether you want to do them as a matrix, or if you want to do it as just plugging it into the calculator, or Gaussian elimination, or whatever. It doesn't matter to me. Just kind of tell me how you do that. So we added some values in, tried on a couple of examples just with those independent current sources, and those are really easy because all they ever do is just tell you specifically what the current is that's rolling into a given node. And again, our convention is going to be that if the current is going into the node, then it's going to get a negative sign. If it's rolling out of the node, it's going to get a positive sign. Dependent current sources, we added those in. Again, just like a couple of lectures ago when we started talking about dependent sources and writing KVL and KCL equations for them, it may seem complex originally to start thinking about these dependent sources, but that's really the same way we're always going to do it is to treat them initially as an independent source, then write a controlling equation in terms of some other components of the circuit, something that already is there. And it's, in this case, what we want to do is write the dependent current source controlling equation in terms of one of the node voltages, plug that in where we originally saw the dependent current source information in the original KCL node equations, and then just sort it all out, solve for it that way, and it's really not that big of a deal. We started talking about independent voltage sources. These might be really, really easy. They might actually be considerably more difficult. When you have the voltage source connected between a reference node and a non-reference node, that's really easy. We know that the node voltage at the non-reference node is the value of the voltage source. It's just how it is. And it's really easy to do that. When it gets harder is when you have that voltage source connected in between two non-reference nodes. And this is about as far as we got this morning when we were looking at these supernodes, which is how we're going to deal with these independent voltage sources connected between non-reference nodes. So we looked at the independent sources, no big deal there. Supernodes are how we got to this, all of this stuff in the first place. And what that's going to do is it's going to reduce by at least one the number of equations that you write for your simultaneous equations. So we just write those, and we went through at least one example of this morning. So let's see if we can do one more. Did we do that one? I think we did that one. Here is a somewhat larger supernode circuit, and let's walk through this one and give you an idea of how this plays out in a somewhat larger scheme. So here we go. Got a 2 kilo ohm resistor here, and here is our problem voltage source. It's sitting here between the nodes that we'll call this one V2, call this one V1, and those are both non-reference nodes, and that's going to cause the problem for us. Have another 2K resistor over here, and another 1K resistor here. So this is 2 kilo ohms. This is also 2 kilo ohms. 1 kilo ohm here. Another 1 kilo ohm resistor here. Finishing things out, I have another voltage source, a resistor, and a third voltage source. Now, I mentioned earlier today in class that one thing that you can do if you start running into a problem with these voltage sources is that one of the easiest solutions is to just say, you know what, I don't want this to be a non-reference node. I declare this to be to be the reference node, and just we're going to change that to V3 just so my notes are consistent. We can just say, I don't want V3, or this node down here on the bottom, to be the reference node. I want V3 to be the reference node. And if I do that, then I don't have that voltage source connected between two non-reference nodes like it is here. No, it's connected between a reference node and the non-reference node. But in this case, that would mean that two other voltage sources were not connected would be connected between non-reference nodes, and we'd have to write at least two supernodes. And we don't want to do that. We want to keep it down to the minimum number of supernodes possible. So the supernode is going to have to exist here between nodes V1 and V3. And so when we start writing our KCL equations, we will write them in terms of some of these other things. And actually, what this boils down to is that now we only actually have to write one equation, because realistically, that node voltage V4 is constrained to be negative 6 volts, and over here, this one's constrained to be 12 volts. So those two don't even need node equations technically, because now they're connected between a non-reference node and the reference node. So we just really have this one voltage, or one supernode that we need to write the equations for. And we'd like to find all the node voltages, doesn't matter how we do that. But the thing that we need to do is write the KCL, write that node equation. So starting here, we've got V1 connected to V2, which was at negative 6 with 2K between them. So we have V1 minus negative 6 or plus 6 over the 2 kilo ohms of resistance. Then going out this top right-hand side, V1 and V4, which is a positive 12 volts over 2K. So that's V1 minus 12 over 2K. Then now we move down, and this is part of the same supernode when we start looking at the three branches that come out of node V3. We've got V3 minus a negative 6, V3 minus negative 6 over 1K. We've got V3 in the reference node, V3 minus 0 over 2K. And then V3 minus the 12 volts at V4 over 1 kilo ohm resistance. KCL says that equals 0. So that's our single KCL equation, node equation that we have to write. But unfortunately, in this case, we have one equation and we've got two unknowns, and so we need one more equation to be able to solve it. In that case, it's describing the difference between V1 and V3 in terms of that 12 volt source. And just like we did this morning, we're going to say, all right, the difference in potential between V1 and V3 is 12 volts. And we express that mathematically by saying V1 minus V3 equals 12. The difference between those two is the value of that voltage source. So that gives us enough information. We can go ahead and replace things as necessary. And let's go ahead and replace it this way, so that say that transform that into V1 equals V3 plus 12. So rewrite that first equation. So we've got V3 plus 12 plus 6 over 2K, and V3 plus 6 minus 12 over 2K, plus V3 plus 6 over 1K, plus V3 over 2K, plus V3 minus 12 over 1K equals 0. Now we've got one equation, one unknown. Life is much better. It works out that if you solve all of this, simplify it, you get that V3 equals negative 6/7 of a volt. Plug that into your calculator, whatever, to convince yourself of that. And if you want to know the other one, you can say, well, V1 equals V3 plus 12, so negative 6/7 plus 12. 11 and 1/7, whatever that happens to be as a decimal. Let's see, 1/7 is irrational, so well, actually it looks like it's 11.1428 repeating. So that's doing a supernode with an independent voltage source, and again, we had to do that because we had this independent voltage source that was connected between two non-reference nodes. It's unfortunate, but if you're going to do nodal analysis and you're going to have these independent sources, it's the kind of thing that's likely going to crop up on you. There's not much you can do about it. So one of the things that you may take away from this, though, is that if you start seeing too many of these supernodes, it may be a signal to you that instead of using a supernode analysis, maybe you should be doing mesh analysis, which we'll talk about a little bit later. Because in this case, the mesh analysis would be pretty straightforward. You would have to write 4 simultaneous equations, but there wouldn't be anything particularly odd or strange about those. So it's a thought. It says, if you start seeing too many of these supernodes, maybe we should try a different way of doing it. So we've talked about independent voltage sources. Now let's talk about dependent voltage sources. Here's a circuit that's got a dependent voltage source in it, and we want to analyze it using node analysis. So resistor, current source, and resistor. So this dependent source is a dependent voltage source that gives out 2,000 times Ix, and that's what the 2K Ix is. Ix is defined to be the current over here that's running through this 1 kilo ohm resistor. And this is not, when we start dealing with currents on the order of milliamps and resistors on the order of kilo ohms, you'll start seeing things like this to make sure that the currents and the voltages kind of stay in the same neighborhood, so that the voltage that's coming out of here will still be on the order of like tens of volts, where this current is still kind of rolling around in the milliamp range. So this independent current source gives us 4 milliamps. This is a 2 kilo ohm resistor up here, 2 kilo ohm resistor here, and we I think pretty clearly see that we've got a node voltage here of V1. This one's V2. So we're going to need two node equations, plus we're going to need some kind of controlling equation. But realistically speaking, when we look at the voltage, the node voltage V1, while it's connected, there's a voltage source that's connected between the non-reference node V1 and the reference node. And so we don't have to really write an equation for it because it's a voltage source. And so we can say very simply that V1 equals 2,000 times Ix. And we don't have to think about it any harder than that. Again, the point is we treat it like an independent source to start with and then fix it as we go. So let's write the other KCL equation at node 2. We're at node 2, so I'm going to make that one first. I'm going to say V2 minus V1 over 2K. That's one current. We're going to say that one's coming out. Ix is going out, and that happens to be the value of V2 minus 0. It's connected to the reference node over 1K. And then we've got 4 milliamps of current that are coming in. So we're going to go ahead and say that equals 4 milliamps. So we've got our two equations, but unfortunately, I think in this case we're going to see that V1 is somewhat easier to define, but we need to write the controlling equation for that dependent source to make it work nicely. And the key thing to look at here is going to be Ix. What other circuit parameter gives us Ix so that when we plug it in here that we can turn it into something useful? And in this case, Ix is the node voltage, or the current is what's rolling through this 1 kilo ohm resistor, and that is the voltage across it, which is the node voltage V2, divided by the 1 kilo ohm of resistance. And for some reason I have 2 kilo ohms in there, but that's not right. Anyways, so you might want to ignore the slide for this one. It says that, and actually that slide looks like it's been fixed, so I guess that's good. So my notes say 2 kilo ohms. Oh well. So so we have all of the equations that we need, and we can start plugging stuff in and kind of fixing it up. We can solve this and finish it off if we want. So we can just, everywhere that we see, and we can simplify this and kind of say, well, V1 equals 2000 times V2 over 1000, or that basically works out to V1 equals twice V2. So we can go back up into this KCL equation and start plugging that in. So we've got V2 minus 2V2 over 2K plus V2 over 1K equals 4 milliamps. That's going to be a negative V2 over 2K plus V2 over 1K equals 4 milliamps. So you can solve that and say, well, 1 over 1K minus 1 over 2K V2 equals 4 milliamps. Divide both sides by that fraction, you'll get what V2 equals, and I don't have that in my notes, but you can move through and you can finish it off. So for what it's worth, V2 equals 4 milliamps divided by 1 over 1K minus 1 over 2K. And whatever that works out to numerically, let's see if we can figure it out real quick. 1 over 1,000 minus 1 over 2,000. 4e negative 3 divided by, oops, my second answer. So V2 equals 8 volts. And for what it's worth, V1 equals 2V2, and so V1 equals 16 volts. And if you wanted to, you could figure out what the current IX is or any of those other things now based on the fact that we know what V1 is, we know what V2 is. So, and again, the whole point, we start out with the dependent source acting like an independent source, write at least one of the node equations, and in this case it was really easy because it was connected between the reference node and a non-reference node. We write the controlling equation in terms of some other circuit parameter that allows us to simplify this down to something actually quite trivial, 2V2. Plug that back up into our original equation, solve for the first parameter, go back and solve for other parameters as necessary. So it's really not too bad as long as you continue to follow the process. And that process will remain very much fixed between now and the end of the class. Whenever you see a dependent source, treat it as independent first, then go back and change it, I guess. Go back and fix it. So, or deal with the controlling equation. Now, one last dependent source. I guess we'll try to do two more quick examples here. Definitely one. What we want to look at here is we have both. The key thing is that we're going to have a mixture of dependent and independent sources, and we're going to have to do a supernode around our dependent source. So it's going to get even messier, but it's just kind of to show you the power of the solution technique itself. All right, so let's even switch colors just for the heck of it. All right, circuit, here we go. 6 kilo ohm resistor, dependent voltage source, inconveniently located. Resistor, resistor, independent source. This one's conveniently located because we can declare that to be the reference node. We've got 6 kilo ohms of resistance up top, 12 kilo ohms right here. This voltage source gives us 2 times Vx, where Vx is declared to be the, the voltage across this 6K resistor. And we've got 12 kilo ohms of resistance over here. This independent voltage source puts out 6 volts. So that's our circuit. In this case, this is another one where it's not going to help us particularly to try to move the reference node, because no matter where we move it, somewhere there's going to be a supernode. So do you want the supernode to be with the independent source or the dependent source? In this case, we're going to leave it with the independent or the dependent source being our supernode. You know, that's just kind of how we decided to do it for this one. So we can take and draw out our supernode. We'll call this one V1. We'll call this one V2, but realistically speaking, it's important to note that there's no difference functionally between V2 and Vx. So we'll just stick that over here as a note to ourselves that there's still more, there's more information there. Then we've got a node V3 here. V3 isn't going to be very useful because we can say, well, V3 equals 6 volts. That's what the independent source is telling us. So those are our nodes. So we can start. One of the first things that you can do is to write the equation that talks about the difference between the two nodes here. Say, well, V1 has a higher potential than V2 by a value of 2Vx. And so if we remember that V2 equals Vx, then we can come down here and say, well, V1 minus Vx equals 2Vx, or V1 equals 3Vx. And that'll be kind of helpful to us later. That gives us another circuit parameter to kind of work with. Again, because Vx is V2, it's a node voltage that we're already going to be solving for. So that's some stuff that we already have to work with. And so realistically, we only have one node equation to write. We're going to write the one equation that's at the supernode. And we've got all of the information that we need to get this back into some sort of nicer fashion. So let's write that equation. So we've got V1 minus V3, which is a 6 volt. So V1 minus 6 over the 6 kilo ohms of resistance connected between those two. V1 to the reference node, V1 minus 0 over 12K. That's it for node V1. V2, we've got the 6K resistor, so V2 over 6K. And V2 and V3, V2 minus V3, where V3 is that 6 volts, so we can cross that out and say 6 up here, with 12 kilo ohms resistance between it, and that equals 0. So we can just pop right in there and say, well, let's replace everywhere we see the V1 with a 3V2. So we got 3V2 minus 6 over 6K plus 3V2 over 12K plus V2 over 6K plus V2 minus 6 over 12K, and say that equals 0. I've got the work all on my notes, so might as well go ahead and finish this up numerically so that you can kind of have it to work with. So we can separate the two constant portions of it, the negative 6 over 6K and the negative 6 over 12K, put those on the other side. That's going to be 6 over 6K plus 6 over 12K. This should be something like 1 milliamp. This should be a half milliamp. Then the common denominator through here is going to be 12. So this is going to be, this should be 6 over 12K V2 plus 3 over 12K V2 plus 2 over 6K 12K V2 plus 1 over 12K V2. So that's 6, 9, 11, 12. Yeah, 12 over 12K V2 equals, again, the common denominator here is going to be 12, so that's going to be, that'll be 18 over 12K. Multiply both sides by 12K, you get 12 V2 equals 18. So V2 equals 3/2 of a volt. When you simplify that out, divide both sides by 12. And then if you want to, you can take this information. If you want to find, if you need to find all of the node voltages, then we know that V1 equals 3 times V2. Once you plug in V2 as being 3/2 of a volt, we see that that's 9/2 of a volt for V1. So we've got both of the node voltages, and it wasn't too bad. The whole point is that we treated the dependent source as being an independent source to start with. And because it was connected between two non-reference nodes, that meant we had a supernode to deal with. Kind of a bummer, makes the math kind of long and hard, but we deal with it. Then wrote the controlling equation in terms of another circuit parameter, which happened to be Vx. It made it very easy, actually, to do that. And we were able to solve for everything all the way through. So That's using a dependent source as a supernode. Um, let's go ahead and we'll finish up this one last example. It's one of the biggest ones that we've got, and we'll work it all the way out just so you're feeling comfortable and with this concept of nodal analysis, because it's not going away anytime soon. We're going to see nodal analysis show up a lot in this first half of the course, as well as in the second half of the course when we start talking about AC circuits. You're going to see nodal analysis show up there because it doesn't lose its validity just because the sources become sinusoidal. So there's a little bit of everything in this particular circuit. We've got independent voltage sources, we've got dependent voltage sources, we've got independent current sources, we've got resistors, and we're going to end up having a supernode as well. So there's pretty much everything in here. So let's finish labeling up all of these sources. This is a 2 milliamp current source. This is a 2 times Vx voltage source. Vx is defined to be the voltage across this 1 kilo ohm resistor down here. This is going to be a 1 kilo ohm resistor. This is voltage V0, and it's kind of in some ways ideally what we're looking for, but it's fairly easy and trivial to find that. 2 milliamp current source here. This is a 4 volt source, and this is a 1 kilo ohm resistor. So we need to start coming up with our nodes, and I think this is going to be V1. This is going to be V2, but just like in the last example, V2 and Vx are the same voltage. There's no difference between those two. And so we'll do most of our analysis in terms of Vx, or in terms of V2, but we know that we'll be able to swap that around pretty easily. If it helps, we definitely need a node V3 here. And if it helps, you can say, well, there's this node V4 here, but it's just connected between an independent voltage source and the reference node, so you don't really need it. This is totally optional. So what can we write to start with? Well, we know that the node voltage V4 is constrained by the 4 volt source, so we can get that one out of the way nice and easily. We need to, again, do a supernode up here, and we know that V1 is at the higher potential by a value of 2Vx, and since V2 equals Vx, we could substitute that back up here and say V1 equals 3Vx, just like in the last example actually, exactly the same arithmetic that allows that to happen. So now we just have 2 equations to write, fortunately. It's a little bit easier because we have 1 equation to write at the supernode, and we got 1 equation to write at node V3. And if we wanted to, if the circuit, what we're asking for is to solve for V0, we could write one last equation, say V0 is the difference between V1 up here, which is the same node as over here, and V3. It's the difference in potential between those two, and that's a 1K resistor up there for what it's worth. So now we can start writing our node equation. So let's start with the supernode. We've got 2 milliamps of current rolling in, so let's stick that on the far right-hand side of our equation. We're going to need to make sure we come over here and we see that there is 1K of resistance between nodes V1 and V3, so V1 minus V3 over 1K. That's that voltage V0. And then coming out this branch, we've got V1 and this V4, which is we've defined as being 4 volts. So V1 minus V4 over 1K resistance equals the 2 milliamps. And so that takes care of this branch, and that branch. So that's not actually all of it. So we need to add on the rest of the stuff for that same KCL equation, that node equation at the supernode for V2. So I shouldn't have written quite so large. What we need to also add into that is the stuff for V2. So V2 minus 0 over 1K gives us the current rolling through this one. And then going this way, we've got plus V2 minus V3 over 1K. And then we can go back up and say, well, that equals 2 milliamps. So that's our first one. Try to clean that up. So cleaning that up just so it doesn't look ridiculous. We've got V1 minus V3 over 1K plus V1 minus V4 over 1K plus V2 over 1K plus V2 minus V3 over 1K equals 2 milliamps. And that's just, again, cleaning up that equation so that it's not kind of ugly and goofy looking. Let's see if we can squeeze on real quick the node equation at V3. So I'm at V3. I'm going to put all of that. That's going to be the first term in all of my numerators. So we got V3 minus V1 over 1K. And again, that's kind of the reverse definition of this V0 voltage. At least the numerator is. We got 2 milliamps of current running in. We'll make that last. And then V3 minus V2 divided by 1K for the resistor here. And that equals the 2 milliamps of current that are running in. So that one's a little smaller, a little bit easier to digest. But these are our two node equations, number 1 and number 2. All right. So at some point we need to start substituting in more interesting values, something that makes our life a little easier. And again, the thing to note here is that since Vx and V2 are the same thing, we can say that V1, everywhere we see that, we can replace that with 3V2. And so we will get our two equations in terms of just V1 and V2, which will be good. One thing that's worth noting is that if you wanted to, and it wouldn't, I don't know that it would be a particularly great idea because it would make the math more complicated, is that if we were really solving for V0, what would be one last step at least is to solve your supernode in terms of V1 instead of V2. But in this case, that makes the math nasty, doesn't it? Because, well, we can redefine this and say that V2, everywhere we see that, we could replace that by V1 over 3. And that just makes this math that's already fairly complicated even more complicated. And you know what? We don't want to deal with that. So I think that it's worth doing the extra step to once we've solved for V2, solve for V1 using that version of the equation. So let's start solving these equations a little bit. Equation number 1, just break up the terms first. So it's kind of handy that everything's over 1K, and so we could really simplify things quite a bit. But let's just break up the terms first to make our lives easier. So we got 1 over 1K V1 minus 1 over 1K V3 plus 1 over 1K V1 minus 1 over 1K V4 plus 1 over 1K V2 plus 1 over 1K V2 minus 1 over 1K V3 equals 2 milliamps. And actually, I wanted to finish that up, but I'm going to toss all of that because it's not really very useful because we didn't substitute any of our information from this equation back in. So let's kind of chuck that work, forget I did it, it's a long day, and rewrite equation 1 strictly in terms of getting rid of all of the V1s by replacing it by 3V2. So we got 3V2 minus V3 over 1K plus 3V2 minus V4, and that's just 4 volts. So let's get rid of the V4s too for 1K plus V2 over 1K plus V2 minus V3 over 1K equals 2 milliamps. So now we can start messing around and simplifying that. We got 3 over 1K V2 minus 1 over 1K V3 plus 3 over 1K V2 minus 4 over 1K plus 1 over 1k V2 plus 1 over 1k V2 minus 1 over 1k V3 equals 2 milliamps. So we've got 3 over 1k, 6 over 1k, 7, 8 over 1k V2, 8 over 1k V2. We got this V3, and we got that V3. They're both negative, so that's minus 2 over 1k V3, and so that covered all of the V3 and V2 terms. The only other thing that we had is this 4 over 1k term. It's negative when we pull it onto the other side. This is going to essentially be 4 milliamps, so we should end up with a positive 6 milliamps on the other side. So that's our simplified equation 1 once we plugged in the information in a useful way and not kind of wasted our time as with the original version there. So here's the first one that you can plug into your equation solver or whatever. So that's the first one. Second equation. We can simplify that one down a little bit easier, but again, we need to substitute in some of the things that we've been working on here. V3 minus 3V2, substituting in what we've learned from our supernode over 1k, plus V3 minus V2 over 1k equals 2 milliamps. Separate that out, that's 1 over 1k V3 minus 3 over 1k V2 plus 1 over 1k V3 minus 1 over 1k V2 equals 2 milliamps. The V3s, we've got positive 2 over 2k V3 plus 2 over 2k V3. And for the V2s, we've got a negative 3 here and a negative 1 here. That should be a total of negative 4. Negative 4 over 1k V2 equals 2 milliamps. So we need this one. This is the final version of that one. What we got in our first equation was 8 over 1k V2 minus 2 over 1k V3 equals 6 milliamps. So there are two simultaneous equations. You plug those in and you solve them. In whatever fashion makes sense to you, what you get is that the voltage V2, which is the same as voltage Vx as you recall, equals 2 volts. V3 equals 5 volts. And if we were to go back up to our original controlling equation here, that V1 equals 3 times V2. What that means is that V1 must equal 6 volts. And that is probably about as hard as nodal analysis gets, because we had lots of complications in this one. We had a dependent source, and not only was that dependent source there, it was also a supernode. The only thing that could have made this harder was to have additional supernodes, and I'm not sure what the point is of creating such a circuit aside from to torture circuit students. So I can think of better things to do with my time. So that is pretty much nodal analysis in a nutshell. I think at this point you should be able to at least try to do any nodal analysis problem in the book and be able to do a reasonably good job at it. And nodal analysis is one of the very most fundamental ways of dealing with circuits. So it should be something you're comfortable with. And I don't think it's a terribly difficult thing. The only thing that can make it hard is dealing with those fractions in all of those node equations with the 1 over 8k or whatever. So that's the only thing that I think makes nodal analysis kind of hard. So let's sum up nodal analysis in 1 or 2 slides here. The first thing to do is to get the circuit all drawn out, find some sort of idea about how many nodes that you actually have in your circuit, and figure out which one is going to be the reference node. And the reference voltage then is going to be 0 volts. intelligent selection of the reference node may save you from having to do something like a supernode. It might help you. In some cases, you're going to kind of be stuck no matter where you put the reference node. So put it in a place that makes logical sense. For the most part, I think that if you were to look at the circuits that I would give you on quizzes or exams, or the kinds of things that you're going to find on the even the homework assignments, for the most part, those are going to have the reference node along the bottom in a very logical place. So then what we're going to do is at all of the non-reference nodes, we'll write out the KCL equations. And for current sources, it's going to be pretty straightforward. Just remember, if the current's going in, it's a negative sign. If it's leaving the node, it's going to get a positive sign. If one of those happens to be a dependent current source for some reason, then go ahead and write out the controlling equations, hopefully in terms of one of your node voltages. That's what we're shooting for. Get a node voltage as the controlling parameter in your equation. If you have voltage sources that are present in that circuit, you may need to put in a supernode if it's connected between two non-reference nodes. If it is a reference node, then hey, that node doesn't even really almost need to be in the analysis because it just simplifies the circuit down, and we know that at that point in the circuit, the voltage is whatever the voltage source is. What that gives you is n-1 simultaneous equations should be in terms of n-1 variables, and then you solve them, and that will give you all of your node voltages, and you're done. So that's nodal analysis, and that's one of the tools that we have for solving circuits. What we'll look at next is loop and mesh analysis, which is in some ways a little easier than the nodal analysis. In other ways, it's somewhat harder than the nodal analysis. I've been told that if you start getting immensely complex circuits, and especially circuits that get to be three-dimensional, and you start seeing like circuit boards with multiple layer circuits, that some of our mesh equations become either invalid or just remarkably hard to solve. So, but nodal analysis will still work in that condition. I don't know if you're ever going to run into that condition or not, but that's what I've been told. When I was a student, I liked mesh analysis better. I felt like I understood it better. At this point, it's kind of a toss-up, and I think, again, like I mentioned this morning, the point is that here's a tool for your toolbox. We've looked at node analysis. Now we're going to look at mesh analysis as a tool. And if, as the old saying goes, when the only tool that you have is a hammer, everything starts to look like a nail. Well, we don't want your only tool to be nodal analysis. Mesh analysis gives us another tool. And it may click with you a whole lot better, and you may find that mesh analysis allows you to get the right answer more consistently than nodal analysis. That's fine. Knock yourself out. Do whatever kind of works best for you. So what we're going to do is we're going to find all of the meshes, and a mesh is a special case of a loop that has no sub-loops within it. We'll take a look at that in a second. But we can write KVL equations around each one of those loops, and that will give us a series of simultaneous equations that we can solve simultaneously. And then we'll have these loop currents running around. Just like we had the node voltages, we can use those branch currents, those loop currents, to figure out what's going on in the circuit. So just in terms of an illustration, to make sure that you're really clear on the difference between a loop and a mesh, is just this. It's a really simple little idea. So here's a little voltage source, and I'm not going to bother labeling a lot of these parameters because it's not important. It's just the picture to make sure that you understand the difference between a loop and a mesh, because it's a very subtle difference, although I'm not sure that it matters a whole ton in the overall analysis, but whatever. a loop we defined earlier when we started talking about KVL in the first place as being any path where a node is encountered only once. And so we can start here and we can go around here and that's a loop. And we can go around here and that's a loop. And we can go around here and that's a loop. A mesh is a special case of a loop that contains no other loops inside of it. So this, running around like this, that is a mesh. This is also a mesh running around here. Around the outside, that is only a loop. It is not a mesh because it contains two loops inside of it. What we are primarily going to be looking for is to do this as mesh analysis and to write all of our mesh currents. And we'll call this one, for instance, maybe I1 and I2, and that gives us the basis for doing all of our our meshes. So, and solving our simultaneous equations. So that is the difference between a loop and a mesh, just for what it's worth. Although I'm not sure that it will come back to haunt you if you don't totally get it. Here is a fairly kind of, again, convoluted and complex, but hopefully not terribly confusing example, which will help illustrate exactly how it is that we can have these various loop currents that we introduce, these mesh currents, that will give us the answer that we're looking for in terms of solving these equations and being able to find the circuit element values that we want. So here is the circuit. It looks like a nice window pane. This gives out some current I1 of t, and this is some R1. There's some current I3 here. There's some current I2 here. I6 here. I7 here. I4 here. I5 here. And this must be I8 over here. And these are defined consistently with what's on the slide. And so let's just pick out a couple of the somewhat interesting ones, and let's see how much this thing picks up the different colors. So what we will always do in all of our mesh analysis is we're going to look at this, and very similar to essentially what you want to do is look at your circuit like it's a window, and for every pane of glass that's going to be in the window, there's going to be that many mesh currents going around it. And so if we look at this, you say there's 1, 2, 3, 4 panes, and that's going to be the number of mesh currents that we're going to introduce. You can introduce those mesh currents to flow whatever way you want. I think traditionally speaking, we make them clockwise, but as we go, I will show you some circuits where it makes sense to try to define them the opposite way. The key thing is to remember to try to do it consistently no matter how you do it. So just looking at some of the easy and interesting ones. In this case, so we're going to call this IA, IB, IC, and ID. So what we want to be able to kind of look at and see is what are these circuit parameter values in terms of the loop currents or mesh currents that we've introduced to this circuit. Because these, as opposed to the node voltages where everything very clearly has a meaning within the circuit, if you were to go stick a voltage probe between 2 points in the circuit at these two nodes, you would find the potential difference between, say, V1 and V2, or whatever those nodes were happened to be named. Whereas these loop currents don't necessarily exist in the real circuit. It's one small difference between it. But in this case, what we see is that I1 and IA are flowing the same direction and through the same part of the circuit. And so defining I1 in terms of one of the loop currents, I1 is simply the same as IA. And that goes both ways. And we'll see how having an independent current source usually makes mesh analysis a little easier depending on the position of the current source. But if we were doing an analysis, a mesh analysis, and we looked at this and we said, well, I don't need to solve or write an equation for I sub A because it's constrained by the value of that current source. It's kind of helpful. I2, this is where it gets interesting, and you have to pay a lot of attention to the direction that the current is defined within the circuit. And so we've defined, for example, I2 is flowing down through this branch. So if we look, there are two loop currents that go through this branch of the circuit. IA goes through it and IB goes through it. And it's important to note that IA and IB are technically flowing the opposite direction. If they're flowing the opposite direction, then it's the difference between IA and IB that gives us the value for I2. And it works, and we put the IA first because it's flowing the same direction as what we've defined I2 is flowing. If we wanted to, we could change the direction of I2, and that wouldn't matter. Perhaps the kind of the interesting one here is we can look down at, say, I5. I5, we can define it either way and say, well, I5 has two branch currents flowing through it. We've got ID flowing through it, and we've got IB flowing through it. We can say, well, IB is flowing the same direction, and ID is flowing the opposite direction. So that gives us the difference for I5. If we wanted to, what I was trying to get at before is that if we had defined, just for the sake of example, if we defined I2 as flowing the other way, then it would be IB A, but that's just a hypothetical, so kind of ignore that. Anything else that's kind of interesting? This is the basic formats of everything you're going to see. Perhaps the other one that's worth kind of noting, I8, for example, it's only got one loop current flowing through it. It's got IB, but IB is flowing the opposite direction that I8 has been defined as flowing, and so it's going to be negative ID. That gives us that. And the point of all of this is to show you that we can now solve for any of the currents running through any of these portions of the circuit once we find out what these mesh currents happen to be. If we know what the current is running through this resistor, well, then we can solve for the voltage across it, or the power that's being absorbed by it, just in the same way that we can do the mesh, or once we have the node voltages, we can solve for anything else. And it says this on the slide, but to put it on the paper too, if we have for n nodes and B branches, we will need B minus n plus 1 equations. Realistically, again, look at the circuit as being a window. Find all of the panes in the window, 1, 2, 3, 4. And in this case, I mean, you could figure out that this more complicated things simplifies down to just 4 nodes, or 4 mesh currents. Now we will look at this in the opposite order that we looked at the other ones, because in this case, in node voltages, and when we're doing nodal analysis, the independent voltage sources would frequently make things harder, and we would have to introduce these supernodes to make it work. In this case, because we're writing KVL equations, our voltage sources are really simple, and we like voltage sources are just constant numbers that show up. So we'll take a look at independent voltage sources, then dependent voltage sources, then we'll look at current sources, because current sources can have the same kind of you can make it way easier, or it can make it way harder. So let's start out by looking at a simple independent voltage source circuit and doing some nodal analysis on it. So the slide shows all of the same work that I'm going to do on the piece of paper, so you can copy that down or whatever you want to do with it. But here is the circuit that we're looking at in the first place, and we're going to look at this just in terms of the circuit parameters as unknowns. instead of working all the way through the numbers. So we've got two voltage sources, we've got a number of resistors in there, and we're going to show you what the KVL equations or the mesh equations look like to solve this. We're going to call this one VS1, we're going to call this one VS2, we're going to call this one R1, R2, no, that's actually R3. This one is R2 down at the bottom, R4 is over here, and R5 is over there. And for what it's worth, all of these things have corresponding voltages on the slide. So R2 has a voltage V2, and R5 has voltage V5, and so on. Okay, so we can just start writing our KVL equations in this case. So you look at it and you say, well, here's a window. It's got two panes in it, so I need two equations to solve this one. So let's draw in our two equations. Again, traditionally we go around clockwise. You can define it the other way. It doesn't matter. It's not going to affect anything except for the signs, and it will all work out in the end. So going around the first loop, we run into the negative terminal of the voltage source, so the negative VS1. We run into V1, then V3, and then we run actually into the negative terminal. Oh, no, I defined this wrong. That's negative, that's the positive terminal. Plus V2 KVL says that equals 0. Now going around the second one, second loop equation, we've got the positive terminal of VS2. We've got the positive terminal of V4. We've got did I define that one wrong again? Yeah. I defined both of those wrong. Negative terminal is over there. So run into the positive terminal of V5. And then we actually do run into the negative terminal of V3. That one I didn't define backwards. But the same kind of thing is going to happen with these when we start filling out what these voltages are. There's going to be combinations of two different loop currents that are going to contribute to the voltage across this, and this negative sign will kind of work itself out if you follow the procedure and the way that I outline you to do it. So what are all of these voltages in terms of something I can use and that I can solve for and that I might be given at the problem setup? Well, the only thing that you can really expect to get are the resistor values and the source values, and that's reasonable. I can put these sources as constant values on the other side of the equation. That's pretty straightforward. But what are the other voltages? Well, V1 is the current that's running through it, and we're going to call this one I1, call this one I2. So V1 is the current I1 times the resistance R1. V2 is pretty easy. We got the current going in, so it's just going to be the same current I1 times the resistance R2. But R3 or V3 is going to be a little bit more complicated because it's got two different currents flowing through it. As the voltage is defined, I can say, well, that is the difference between I1 minus I2 times R3. Now I can come over here, do the same kind of thing. The source has a constant value. V4 just has I2 running through it times the value of the resistor R4. R5, same kind of thing, just has I2 running through it. Now here, this is again where I want you to kind of say, we know what V3 is, but what I would really like to kind of see you do is to say, well, V3 is the voltage, or is the current I2 minus I1 times R3. Now, again, if we do it this way, now we're going to chuck that negative sign, and we're going to make it a positive sign. And kind of why that works is that I have multiplied this by -1 already. And that's what switched this from being, so this is really negative V3 here on the right hand side. On the left hand side is V3, and that allows me to not worry about did I assign this the positive polarity or the negative polarity, but I just always think I put the current that I'm working on first inside of this subtraction, then I will always just, the signs will work out. Just like in nodal analysis where I said always just, I'm working at node X, so I'm going to put node X first. Here I'm working with loop current 2, so I want loop current 2 to be the first thing. The numbers will all work out. So now we've got two simultaneous equations in terms of two unknowns, just I1 and I2. We simplify, we solve them simultaneously, and that gives us our answer. And all we have to do is plug in the various resistor values, and that gives us an answer. So let's look at an answer, or one problem at least, that has some numbers in it. So here is 12 volt source connected with a 6 kilo ohm resistor. There's another 6 kilo ohm resistor here, 3 kilo ohm resistor, and a 3 volt. That's a plus and a minus on a 3 volt source. And kind of the key parameter that we want to solve for here is I0, and 6K resistor, 3K resistor, 6K resistor. Now, if we look at this, kind of what you should think at least a little bit is, what would this be like as a nodal analysis problem? Because, you know, you could be, when I give you a quiz or when I give you an exam, I'm just going to throw you a circuit and say, tell me what I0 is. And you have to decide, well, is this a nodal analysis problem or is this a mesh analysis problem? Which one will get me to the answer easiest? In this case, well, as a node problem, this is probably pretty easy. We've got two independent voltage sources, but if we just say, well, here's the reference node, we've got one equation to write because we know what the voltage is here, we know what the voltage is here, so we've just got one equation to write, one unknown to solve for, and it's pretty straightforward. So this might not be a really great problem to do as a mesh problem, but we're going to do it that way anyways, just to kind of show you how it works. We're going to introduce two loop currents, and we're going to say here's loop current I1, here's loop current I2, and we will start writing equations going around each one of those loops. So for the first loop, we run into the negative terminal of the 12 volt source, we run into the 6K resistor, and so we'll say, well, that's 6 kilo ohms times I1 gives us the voltage across that 6K resistor. And now notice, like in the last problem, I had all of these polarities of voltages sitting around. I'm not even putting them in. I'm not worrying about them. I'm throwing them away, and I'm just going to always say I'm going to put the current that I'm working on first. So when I get to this 6K resistor in the middle that has both of my loop currents running through it, I'm going to say, well, it's 6 kilo ohms times I1, because I'm working with that one, minus I2. The KVL says that equals 0, so that's our first equation. So let's start on the top here and get to maybe the harder part later. So this 3K resistor just has I2 running through it, so the voltage across it is 3K times I2. We run into the positive terminal of that 3 volt source, and then when we get to the 6K resistor, this is where it's combined, this is where the currents are flowing opposite directions and all that stuff, and you know, in theory, we kind of sort of say, well, there's a plus sign here and there's a negative sign here because that's how I defined the voltage here. But you know what? I don't like having those there. Let's forget that they exist. Let's not put them in there at all and just say, look, there's a 6K resistor and I'm working on current I2, so I'm going to put that one first. And as long as you do it that way, the signs will work out. So those are our two equations. We can simplify them a little bit. We've got 6K here and 6K I1 there, so that gives us 12K I1. We've got a negative 6K I2, and that sums to 12. Here we've got just a negative 6K I1 and a 9K I2 plus 9K I2, and that equals negative 3. Now, and that's it. Now you plug and chug. You put the information in for the that's all you need for your simultaneous equations. Put that into your equation solver or whatever, and that looks a lot cleaner than the nodal analysis, I think. You look at that and you just have these everything. There's no fractional coefficients on any of these currents. It's all just 6K, 12K, positive, negative. It's certainly a lot easier to write those equations out and to get perhaps the right value. But you can run into the same kinds of math problems that you run into with other things. I don't actually have this one solved, so let's solve it real quick. Two equations. We've got 12,000 as the first one, negative 6,000 as the second one, and 12 volts as the solution. Negative 6,000, positive 9,000, negative 3, solve. And what you get is that I1 equals, let's see, that would be 1.25 milliamps, and I2 equals half a milliamp, 0.5 milliamps. And so then in terms of these loop currents that we've created, I1 and I2, if we wanted to find out I0, for example, I0 is just I1 minus I2, and so that's going to be, what, 3/4 of a milliamp? Yeah, 0.75 milliamps. And then we know the current that's running through everything in this circuit. We want to know what the power in the 3K resistor is, for example. Say power 3K. That's just going to be the current I2 squared times the resistance of 3K, for example. We could do that, or we could do anything else. We've got all of the information that we need to solve that. Let's just do one more example. Maybe, let's see, we've got... Let me do two more examples. One where we add in some, one is a little bit more complicated voltage source example. The other one has a current source in it, and so I'd like to cover that at least once before we're done today. So, here we go. Mesh analysis example number 1. Here's a circuit, voltage, let's see, no voltage source. Another voltage source, and we got a 6K resistor. So 6K here, the 6 volt source, 3 volt source, 2K resistor, 4K resistor, 2K resistor. Now this one, when we look at this, and the parameter that we would like to solve for, we're going to call that V0, which is the voltage across the 6K resistor. Now this one, we can look at it and we can say, yeah, this one's probably better as a mesh example instead of a nodal example, because somewhere, regardless of where we put the reference node, we're going to have a supernode. And so for that one, you might say, yeah, let's do this one as a mesh equation. It makes more sense, at least in my book. So let's define our loop currents. There's going to be 2 of them. You look at that, you say, all right, there's 2 panes in the window, this one and this one. So here's our loop current I1. Here's our loop current I2. We are done defining loop currents. Start writing our KVL equations around here. So we've got 2K times I1. We've got 4K times I1. We've got 2K times I1 minus I2, because that one's shared between these 2 loop currents. And then we run into the positive terminal of the 3 volt source. 3 volts equals 0. So that's around the first loop. Going around the second loop, we've got, well, we run into the negative 6 volt terminal first. We've got 6K times I2. Then we run into the negative terminal of the 3 volt source. And then, again, you can think about it. You can say, well, I've got these polarities. Just forget that. Just say I'm working with I2. So we've got 2k I2 minus I1. Just put the node or the mesh that you're working with now, put it first, sum it to 0. So those are your two equations. Let's simplify those. Just for reference, we'll call them equations 1 and 2. So we've got 2k, we've got 6k, we've got 8k times I1. We've got just negative 2k times I2, and that equals negative 3. For I1 on this one, we've just got negative 2k times I1. And then we've got positive 6, positive 2, so we got plus 8k I2. And that equals, there's a positive, negative 6, negative 3, so we get a positive 9 on that side. So you solve that. I1 equals negative 0.1 milliamps. And I2 equals 1.1 milliamps. And what we wanted to solve for in the first place was this voltage V0, which gives us the voltage across the 6K resistor. V0 is simply 6K times I2. And so that is 6.6 volts. And I think in some places, that happens to equal 33 and over 5 volts. For those of you who have the TI-95s and other pretty print calculators, you might see something like that come across as your answer. So that's a simple mesh equation. Perhaps you look, again, you look at this, and there's two things to think about. One is that this analysis does seem to be somewhat simpler because you don't have a bunch of fractions. It's a little bit harder to screw up the math here. And again, it's worth looking at this and realizing that this might not be a very good nodal analysis problem because somewhere there's going to be a supernode. In this case, it works out pretty nicely as a mesh analysis problem. One more for the sake of completeness, and we'll come back and look at more at this mesh analysis stuff, especially with the dependent sources and with the super meshes next week. Here is a mesh analysis problem that has a independent current source in it. Now, just like your independent voltage sources can make your life a little easier for for nodal analysis, they can make your life a little, or these independent current sources can make your life a little easier for mesh analysis. So we've got this 6K resistor hanging out here. We've got a 2-volt source, we've got a 2K resistor, we've got a 4K resistor, and we've got this 2 milliamp source. This is an example of where life can be a whole lot easier because when we define our loop currents and we say, here comes loop current I1, here comes loop current I2, well dang, it is not possible for the value of I1 to be anything other than 2 milliamps. It just cannot be because it's constrained to that value by that current source. And so just like if you have a voltage source that's connected between a non-reference node and the reference node, and we don't really have to think about it, here we don't have to think about it either. We just say, you know what, I1 is 2 milliamps, and we're done thinking about that one. And so then we only really have to write the one equation over here on the right-hand side. For the right-hand pane, we get negative 2 volts up at the top. We get 6K times I2. And then we get 2K. I'm working with I2. I'm going to put that one first. I2, let's just jump right in and say minus 2 milliamps equals 0. And then we can go ahead and solve, or simplify and solve this equation. The 2K and the 2 milliamps will, the kilo ohms and the milliamps will kind of cancel each other out, and it'll end up just in the volt range. So we'll get negative 4 there, negative 6, put that on the other side, get a positive 6 on the right-hand side, and a total of 8K I2 on the left-hand side, and that equals 6 volts. So I2 equals, I guess that's 3/4 of a milliamp, 0.75 mils. And then the parameter that we wanted to solve for, V0, was just 6K times I2. So 6K times I2 is 4.5 volts, it happens to be. So that's, I mean, that's kind of as hard as it gets, I guess. You know, there's not much more going on there. So now, let me set up for you a problem where life gets a little bit more difficult, and why we're going to run into problems with these independent current sources. So I'm going to skip the values, and I'm just going to kind of draw up this circuit, show you what's going to happen. So note here. So here's the circuit, and so we say, all right, well, there's 3 panes in this window, and I will define this current going around this way, I'll define this current going around this way, and I will, you know, I can try to do this and say, well, that's, I really want this one to be I1, and I really want this one to be I2, because then I don't have to think at all about these equations, because they go the same direction as those current sources. There's a problem, though, and it's with this current. This is not going to work, and it's bad news, because this current source cannot possibly just take on the value of this, or this loop current, I3, cannot possibly just take on the same value as I2. It's not possible. It can't just be a negative I2. The circuit won't, you know, the configuration doesn't allow for that. And so what we need to do is find a different place, a different way to route I3 so that it doesn't run into this problem with this, this current source. And that's where this, we need a super mesh. And we'll start talking about super meshes on, I guess, next Monday. So again, kind of pay attention. So that should get you started on any homework assignment that I would assign. Look for that to pop up, you know, sometime soon, whenever I get around to doing that. And the homework assignment, or the solutions, will be posted again also as soon as I get around to it. I will email you guys if there's going to be that time on Thursday where we're going to meet here. See if I can't get you guys some donuts or some other mug goodies out of it or something. And yeah, watch for a quiz covering, we'll probably focus on the nodal analysis, write up something fairly straightforward for that. So I guess that's it for today. Again, don't come to class on Tuesday or Wednesday at all, and probably not much of Thursday either, if at all. So we'll definitely see you guys next Monday, and have a good weekend. Yeah, see ya.